Today's the big day. I'm gonna hug some trees. Okay, backstory. My friend Isabel is always roping me into things, and today that means making sure sequoias in our nearby forest are growing appropriately. My job is gonna be pretty simple. All I have to do is hug some trees to figure out how tall they are. Isabel thinks this is gonna be really hard, but I'm not fazed because I know that two directions, like width and height, can be related. The trees need someone to speak for them, and I am here to help. Hi, I'm Sabrina Cruz, and this is Study Hall, real-world statistics. This isn't the first time I've gone on a tree data mission with Isabel, but back then we were measuring both height and width. To collect data, I figured out the circumference of the trees and then their width. Isabel, meanwhile, used their superhuman climbing skills to scale several towering coniferous majesties. We wound up with one width and one height value for each of the gigantic trees we looked at. Those data pairs then became points on a scatter plot, and we saw a pattern emerge. Wider trees tended to be taller, and narrower trees tended to be on the shorter side. That's what we assumed, and everything seemed great. But now Isabel has to measure more trees. They're tired and they do not want to climb more sequoias. And I'm not here for my verdant skills as an arborist. I'm the numbers guy, safely on the ground. But I also know there's a way we can already understand the relationship between tree width and height in the whole forest. And when I'm done, Isabel can keep measuring just tree widths and use the data to predict tree heights. It'll save them time, and I'll be the hero. With that, we come to the tree of knowledge of introductory statistics. It's the critical shade giving you relief from the sun, the carbon sink absorbing greenhouse gases. We have arrived at regression. Regression helps us understand the relationship between two quantitative variables, like tree height and tree width. It helps us predict a dependent variable y, here tree height, using an independent variable x, here tree width, by describing the relationship between them as a line on a graph. We find this line by regressing y on x, tree height on tree width, and we describe it as a simple regression equation. In this equation, the letter a is the y-intercept. It represents the predicted value of the dependent variable when the independent variable is 0. In this case, it's predicting how tall a tree would be if it had a width of 0. A lot of times, that intercept doesn't make any sense. This line tries to get as close to all of these points as possible, and in doing so, it has to cross 0 at some point, and a tree with no width wouldn't exist at all. But this intercept does help us mathematically describe the full relationship between tree width and height. The letter b in the simple regression equation is the slope. It represents the rate of change in the dependent variable for a 1-unit change in the independent variable. If a tree increases in width by 1, we expect to see a 1.05 increase in tree height on average. Here our slope is positive, which makes sense. Wider trees are usually taller, and that's what we saw in our original plot. But in different cases, the slope might be negative, like if we are predicting mistakes on an exam from time spent studying. An increase in study time can be related to a decrease in errors. And if there is no linear relationship between our independent and dependent variables, we expect our slope to be 0. Like knowing how much it rained today probably can't help us predict the cost of tuna at the grocery store. Moving on, that error term in the simple regression equation is there to remind us that no line will perfectly describe the data. There's going to be a little variation between the predicted value of a plus bx and the true value of y, and that's okay. That also means one line rarely exactly touches every single point. It's above some points and below others. The key is that it's as close as possible to the points overall. The line minimizes those errors. Okay, so that's all great, and we are on our way to summiting the heights of even the mightiest sequoias. But maybe we want to know how strong the relationship is between tree height and width. Sure, we care about predicting an individual tree's height from its diameter, but it's also good to know how reliable that prediction might be. To suss that out, we'll need the coefficient of determination, denoted r². This value measures the proportion of all the variability in tree height that is explained by tree width. Basically, that tells us how much of the wiggling around in tree height we can predict based on our knowledge of tree width. So if tree width perfectly predicted tree height, our r² would be 1, meaning that 100% of the variability in height is explained by width. Alas, nothing in life is ever that easy. Our r² is 0.27. That means that 27% of the variability in tree height is explained by width. That's not super high, but trees are complicated. Believe me, I've read the overstory. It would actually be surprising if only one variable told us everything. But that line is still describing an important part of the tree's growth story. It's worth taking a deeper dive into this relationship before looking for other independent variables that might help explain tree height. Okay, so far we've used regression to describe the relationship between tree height and width, but we can also use regression to infer things beyond that, and I think we could use the regression line to predict tree height based on tree width. But we still have some work to do. We need to know if the relationship between tree height and width is even statistically significant, or if we could make better predictions some other way. I know that 27% of the variability in height is explained by width, but I want to double check that we couldn't describe tree heights just as well by, say, just predicting the average height over and over. Inference can tell us whether we're getting enough bang for our buck, and using regression to do inference requires a hypothesis test. Here we're trying to understand if our independent variable, tree width, does a good job describing our dependent variable, tree height. That means our null hypothesis would be that our tree width does not describe tree height well. The alternative hypothesis would be that tree width does describe tree height well. Then we let the computer do the work. We use our software's function for linear regression, specify which column in our spreadsheet represents the dependent variable and which represents our independent variable, and then let it do the rest. The computer compares how well tree width describes the variability in tree height compared to just predicting the average height for every tree. It gives us a test statistic of 10.71. We use that number to find the p-value. The probability distribution that we need here is the F distribution. Here the numerator degrees of freedom is 1, and the denominator degrees of freedom is the number of data points, here 31, minus 2, leaving us with 29. You can think of it like we're losing 2 degrees of freedom because we're estimating 2 values, the slope and the intercept. We can use software or an F-table to find our p-value of 0.003. We interpret the p-value like we always do. This small of a value means we reject the null hypothesis and can conclude that tree width is a good predictor of tree height. Proving that is an important step towards actually being able to help Isabel out. Still, let's cool our jets for a second. Our alarm bells should be ringing louder than birds up high in an eastern white pine. We need to check some assumptions so that we can trust our conclusions, and a lot of that can be done by looking at images. First off, regression is good at describing linear relationships. If the relationship between tree width and tree height isn't actually linear, then even our best line isn't going to do a good job of describing what we're seeing, and we probably need a different tool. But we can figure that out pretty quickly by looking at our data in a scatter plot and making sure it's linear-ish. It doesn't have to be perfect, but there shouldn't be any obvious curves. If we do see some curvature, then there are other tools we could use, but we'll get to that in other episodes. If our lines look decently straight, there are still some other assumptions we need to check. But first we need to revisit the error term in our simple regression equation. Remember, that's there to remind us that no line perfectly describes data, and we can keep track of all the different ways the line deviates from our points by measuring the vertical distances between each point and the regression line. These differences between the observed values of the dependent variable and the predicted values of the dependent variable are called residuals. So for the tree whose width we measured as 8.3, we predicted its height to be 70.78, but the true height was actually 70. That makes our residual for that point 70 minus 70.78, which equals negative 0.78. Now the regression line overestimated the height for this particular tree, but looking at residual values across all of our trees helps make sure that we're on the right track. See, residuals as a whole tell us how far off our predictions of tree height are from the actual heights we measured. If there are patterns in the residuals, our line might not be capturing what's important about the relationship between the two variables, and that could mean we haven't met our assumptions. Knowing that is important. Our assumptions are what allow us to make accurate inferences, and we need that to trust that our results are meaningful. Which leads us to some assumptions we need to check. First off, we want to make sure variability is similar for all different values of the independent variable. Like if Isabel's predictions are doing pretty well for small and medium-sized trees, but they are way off for large values of tree widths, that isn't ideal. That would mean that our line is not describing the full spectrum of trees equally well. This situation would be called heteroskedasticity, which just means different variance. But since we want to account for each tree equally, linear regression assumes we have homoskedasticity, which means same variance. Having homoskedasticity means that we won't run into the problem we just described. We can check for homoscedasticity by plotting the independent variable on the x-axis and our residuals on the y-axis. We want to see roughly equal numbers of points above and below 0 and have the width of these points be roughly the same as we look left to right. Basically, we want to see a rectangle. Now, ours isn't quintessentially blocky, but it seems reasonable, which is good news for Isabel and also for me. I have one job, and I cannot screw it up. We also want most of our residuals to be small, with roughly equal numbers above and below 0. We call that normality of residuals, and it helps us ensure accuracy. To check that, we can make a histogram of our residuals and look for that bell shape that we all know and tolerate. And good news, our residuals are roughly symmetric around 0 with a bellish shape. That's most of our assumptions checked, but it's worth mentioning one more that we won't get into in this course. That's the assumption of independence between the observations, which requires some context about the data. In our case, Isabel tells me that we don't have any reason to suspect that the height of one tree impacts the height of another one, so we're good to go. Now, you're not completely out of luck if certain assumptions aren't met. We won't get into them now, but other options exist. In my case, though, we figured out that tree widths are positively related to tree heights. So Isabel can focus their attention on using width to predict height, avoid scaling terrifyingly large trees, and I can bask in the satisfaction of being the best friend ever. Whether you're trying to speak for the trees or looking at something like training and job performance, regression helps us predict and understand relationships, and checking assumptions helps us trust our results. Imagine if I told Isabel that we were good and we weren't. The trees wouldn't be properly measured, and I would have failed at my one job. But the real takeaway here is that regression is used all over in fields from science and math to the humanities and beyond, because it's normal to want to know how two things are related. A family tree of connections, if you will. If you're enjoying this series and are interested in taking the full study hall real-world statistics course and earning college credit from ASU, check out gostudyhall.com or click on the button to learn more. And if you want to help us out, give this video a like, smash that subscribe button, and comment if you speak for the trees. Thanks for watching, and see you next time.